What's up, scholars? We're going to go through some quick notes here on the greenhouse effect. So the greenhouse effect is simply where gases in Earth's atmosphere trap heat and make the temperature of the planet warmer than it would be if those gases were not present. Now we're going to talk a lot about this. It turns out we do need the greenhouse effect, but we don't want too much. So basically what happens is the light from the sun passes through our atmosphere. The atmosphere is transparent to that sunlight. And then what happens is the Earth will absorb that energy and then re-radiate it into the atmosphere. Now the greenhouse gases will actually block those greenhouse gases, or rather the energy, it'll block the energy from getting out of the atmosphere, acting kind of like a blanket, acting like a blanket. So you have experienced this almost certainly. Let me move my face here, perhaps. Have you ever noticed that if you leave a car in the sun in a parking lot during the summer especially, it can get really hot. For example, here it says it's 80 degrees outside, but close to 100 degrees on the inside in just 10 minutes time. What happens is very similar to Earth's greenhouse effect. The sunlight is transparent to the glass. So the sunlight coming from the sun passes right through the glass like it's not even there. Then it hits the interior of the car, like the seats and the dashboard and stuff like that. And then it re-radiates as infrared energy. So it's lower energy, and it just so happens that that lower energy light that's re-radiated from inside of the car gets blocked by the glass. So it comes in, but it can't get out, and so all that energy is trapped inside, and it increases the temperature of the car. That's why it can be dangerous to keep things like dogs or small children inside of a car, because it can get really, really hot. So this is also literally used in greenhouses. This is the conservatory or greenhouse at Garfield Park here in Indianapolis on the south side. And they can grow plants in the winter, which is really helpful. So how does the greenhouse effect work? I want to explain it and then show you exactly how it works with a little simulation. So CO2 is the most important. That's the one we're going to focus on right now, but they all basically work just like this. Again, the CO2 molecules, instead of the glass, the CO2 molecules are the things that are transparent to visible light. And then what happens is that sunlight that passes through the atmosphere, passes through the CO2 on the way down, gets absorbed by the land, just like in the car, and then also by the oceans. And then the CO2 absorbs that re-emitted infrared light, acting, again, just like a blankie. So I want to show you what that looks like in a little simulation. What I've got here is a little simulation that's going to shoot. We'll start with visible photons at our CO2 molecule, and we'll see what happens to, get rid of that. We'll see what happens to the visible photons when they go by the CO2. Let's watch what happens. Okay, so you can see right here, now that those infrared ones are out of the way, the visible photons are just passing right by the CO2 like it's not even there. Just like light, visible light passes right through glass, like it's not even there. Now what we'll do is we'll switch over to infrared photons. We'll let those. So infrared photons, watch what happens. They smack into the CO2 and sometimes they'll get absorbed. Some of them are going past, you'll see, some are going past. But it'll get absorbed and then re-emitted. So this is how it behaves. Like a blanket, it will block some of that heat. Infrared light is basically just heat. It will block it from leaving the atmosphere. So I'm going to show you a couple of other models of Earth. This one pretends like instead of CO2 in our atmosphere acting like a greenhouse, we literally put a greenhouse over the Earth. We add glass layers. So what we're seeing here are visible photons coming from space, and we're seeing this infrared light is re-radiated. It hits the ground, the sunlight hits the ground, the yellow light hits the ground, and then that red light here, that's infrared, it's basically heat energy leaving Earth. It is, you can see right now as it leaves Earth, it's actually cooling the surface of the Earth off. In fact, Earth would be something like 0 degrees Fahrenheit if we had no greenhouse effect. Now, I'm going to add a pane of glass here, and we'll see what happens to the temperature. So now what I'm going to do, the same process is going to happen. I'm going to turn off some of these photons. So watch these infrared photons. Some of them are going to hit that pane of glass and then be bounced back down or absorbed. And what you're going to notice is that the temperature of the Earth is going to climb. So I've added a layer of glass. Now this isn't real. In real life we have CO2 instead of glass. But you can see pretty dramatically the temperature of the Earth is going up, which turns out a problem. So this is a slightly more realistic picture. We've got sunlight coming from space. We let that sunlight come down. It's going to pour down and hit the surface of the Earth. Notice right now it's very cold. We are using today, or whenever this was made, around 400 parts per million of CO2. So you can't see the CO2. Notice it just looks like we've got our atmosphere. This is nighttime. And what we're going to see is after those visible photons from space, from the sun, hit the ground, that you're going to see the temperature actually start to warm a little bit. Watch these infrared photons. They're going to get absorbed on their way up. They're not going to escape into space. If they just escaped into space, then it would get very, very cold here on Earth. I'll show you that in just a moment. But instead, the temperature goes up. It's a balmy 60 degrees or so on average all around the Earth. So thank you to the greenhouse effect. If it wasn't here, we would basically have an ice ball Earth. So we've gone into some detail about how the greenhouse effect works. And I want to talk to you about how we do really need the greenhouse effect. If you had, like Venus, it's about 96% carbon dioxide. Its atmosphere is 100 times thicker than ours. This was the first place that we studied climate and the impact that CO2 and greenhouse gases can have on a global planet scale. And what we learned is that the average temperature on Venus is something like 900 degrees Fahrenheit or 450 degrees Celsius. So to be clear, there weren't living things that we know of on Venus that made the amount of carbon dioxide go completely through the roof. It has a lot to do with the volcanoes on the surface of Venus. But anyway, here's a quote from Neil deGrasse Tyson, a famous astrophysicist. Basically, he says that Venus is 900 degrees. It can literally melt lead. That's also like saying you can cook a pizza on a windowsill in 9 seconds on the surface of Venus. So it is just crazy hot there. We do not want a greenhouse effect like Venus has. In fact, Venus, if you look here, we've got this image taken through these thick clouds. The image on the right, you can actually see ancient dried riverbeds. So we really don't want a greenhouse effect the same that Venus has. Now, to this point, we don't think that humans will contribute to climate change to the level that the oceans will boil off. There's just not enough CO2 here that's readily available to put in the atmosphere to do that. However, so this is just dramatic over exaggeration. However, the impact that we're having on the greenhouse effect is accelerating. So we're speeding up the warming. Not just warming, but we're speeding it up. So let's not contribute to speeding up that process even more. Now, on the other side, you'd have an ice ball Earth without the greenhouse effect. So like Mars, its atmosphere is very thin. It's only 1% the thickness of ours. So there's very little greenhouse effect. It's essentially a cold, dead rock that we know of. Now, there used to be an atmosphere on Mars. There even used to be liquid water on Mars, but there isn't anymore. So we don't want to end up like Mars either without a greenhouse effect. We want just enough. The average temperature on Mars is about negative 80 Fahrenheit. And you can do the calculations, and scientists do this. And the Earth, without the greenhouse effect, would be around 0 degrees Fahrenheit. That's about as cold as it ever gets here in Indianapolis in the wintertime. And it would be like that essentially across the entire Earth. It would not be good. With the greenhouse effect, the average temperature across the entire north to south pole on the Earth is around 60 Fahrenheit, which is manageable for life. So the last couple things here. First, we'll talk a lot more about this, and especially this graph, but humans have contributed. We have increased by a little bit more than 40% the amount of CO2 in the atmosphere. So before the Industrial Revolution, before we had cars and factories and all that kind of stuff, and lights and power in everyone's home, the CO2 in the atmosphere was around 250 parts per million, ppm. That means for every million particles of air, there are 250 CO2. So it's not very many. And we've just increased it slightly from 250 to about 410 parts per million in 2001. There's an observatory that actually measures this pretty much every single day out in Hawaii on one of the mountains there, Mauna Loa. And you can see that since the 1960s, the amount has gone up, and in fact, it's actually increasing in the rate that we're adding CO2. Here's the last thing. You should know that human-caused climate change is driven by our emission of CO2. There are other important greenhouse gases, but this is the most important greenhouse gas. You can see here, the amount of CO2 actually does fluctuate. We'll talk about how we know that, but it has jumped to just an alarmingly high number nowadays. So the last thing I want to do is give you a quick rundown of the greenhouse gases we are going to study. We're primarily going to focus on carbon dioxide, but you've got carbon dioxide, you've got methane, you've got nitrous oxide, ozone, water, and chlorofluorocarbons. You can pause the video and write down the sources of these, but CO2, the part that's contributing to climate change, we call that an anthropogenic increase. Anthro meaning man, so it's generated by man or humans. So CO2 comes from life, from agriculture, so plants, so cows and things like that, as we raise them, that contributes to CO2. And then also all of the lights that we've got on, all the power that we generate, or most of it, is from burning coal or other fossil fuels. So burning fossil fuels contributes to carbon dioxide. Methane both occurs naturally and it can be added to the atmosphere by humans. It also comes from agriculture, and when we try to burn natural gas, sometimes we leak methane into the atmosphere. Nitrous oxide is not a huge concern, but it is a greenhouse gas. It's both produced by bacteria and by humans, so it's sometimes an anthropogenic increase in the amount that we have. Ozone, it's just up there. It actually protects us from UV light. We like ozone. Water, it's complicated, but basically water both adds to climate change and reduces it for reasons we'll discuss. So don't worry too much right now about carbon. And then chlorofluorocarbons, we actually banned them in the 1970s. So when people talk about action on climate change, we noticed that chlorofluorocarbons were actually reducing the amount of ozone. It was putting a hole in the ozone. It's really bad. So we actually, as a global community, banned chlorofluorocarbons. They're something that were used in aerosol cans way back in the 1970s. So action on climate change can take place. We can reduce the amount of CO2. So that's it, scholars. That was our brief introduction to the greenhouse effect and why it is a big deal. It's increasing the temperature of our planet, and we are accelerating the rate of CO2 that we're pumping into the atmosphere. So that's it for that, folks. Have a great rest of your day.